Good afternoon. I'd like to welcome you to this breakout session. We're going to make Azure Sphere real for you, okay? I am Galen Hunt. I founded the Azure Sphere program, and I'm the managing director of the Azure Sphere program at Microsoft. Joining me on stage in a little bit will be Mike Hall, who's he calls himself a principal software architect today. He changes his title every day. And he's going to show you, we're going to give you a brief overview of Azure Sphere, and then we're going to demo it live, and we're going to show you what the development experience looks like and give you the full deep tour, and then we'll answer some questions. So with that, let's get started. We are taking Microsoft into a swim lane that we've never been in before, and these are microcontrollers. A microcontroller is a single chip computer. Literally, it has the processor, it has memory, it has storage, it has I/O peripherals, all on a single chip. And these microcontrollers are ubiquitous today. There are 9 billion new devices are built and deployed every single year that are powered exclusively by a microcontroller. And it has been a market that Microsoft never cared about before, frankly. Okay, and we didn't care because these are really, really small computers. Your PC, the MPU in your PC has 100 to 1,000 times the power that the microcontroller in your refrigerator has. Okay, and these were also disconnected devices. So we never saw them on the cloud. We never saw them anywhere else. It didn't really matter. That is all changing very, very rapidly. Okay. And it is changing because MCUs, when they gain connectivity, fundamentally change the devices that they're part of. And here's my simple way to describe it. Each of you has a refrigerator at home. And you ask the question, how do you know that the compressor in your refrigerator has gone bad? Well, today you know because you go home and the milk is spoiled and the ice cream's melted. Okay? But imagine a different future, a future of connected ambient intelligence. And in that future, you know that your compressor is going bad in your refrigerator because you receive a message from the device manufacturer saying, hey, you may have noticed your fridge is making a funny noise. That's because your compressor is worn out. We're going to have a technician in your neighborhood this evening with the right replacement part. Could they stop by and fix it before it causes you any trouble? Okay? You think about that experience. That is a profoundly better customer experience than the experience you have today. And the difference is literally a couple of dollars of electronics in the microcontroller to add connectivity and some ambient intelligence and cloud connectivity around that. Okay? And for the last 2 years, I've been out talking with device manufacturers across this whole spectrum of devices, everything from toys to home appliances to industrial equipment, et cetera, that have microcontrollers in them. And as I've talked to them, they all have their list of reasons why they want to add connectivity for their devices around building better experiences, building new business models, etc. What is holding them back is not the lack of radio technology. What is holding them back are security concerns. And we've all seen headlines about fridges sending spam and baby monitors being used for nefarious purposes, etc. I like to talk about this event, the Mirai botnet attack that occurred in October 2016. This was about 100,000 internet-connected devices, predominantly security cameras, ironically, that were taken over by hackers. And by the way, it was very easy to take them over because they all had literally the same password, ROOT. Okay? And so they took them over and repurposed them and turned them into a botnet. They took that botnet and they launched a distributed denial of service attack against DYN, one of the major DNS providers in the United States. The effect of that was to knock the East Coast of the United States off the internet for a day. Okay? And it was a watershed moment. Okay? I think for consumers, it hardly even blipped a register. But for these device manufacturers, this was a watershed moment. And this is the way I'll describe it is, this is the first time the people in the C-suite realized that IoT security mattered. That if you build an IoT device and that device becomes compromised, it's taken over by a hacker, it's not just a problem for your customer who bought that device. It's not just a problem for you. It is a problem for society. And that is because that device can be turned into a weapon. Either a digital weapon, as happened in this case, or a physical weapon. Here's the way I'll describe it to you. The difference between a gas-powered stove and a bomb is a simple matter of software. So, you're a device manufacturer. You want to build connected devices, but you want them to be secure. What are you going to do? Okay? Well, one of the things you can do is turn to other people who have experience. In Microsoft, we have deep experience in what I call the internet security battle. This is the battle that you join as soon as you take a device and you add connectivity and bring it to the internet. Because guess what, folks? And you all know this. The internet is not a secure place. It is not a place governed by laws or rules or anything else. Okay? It is a very lawless place, and it's full of many nefarious people. This is a battle we have been fighting at Microsoft for decades. I think, if I look right, I think tomorrow is my 21st anniversary working at Microsoft. That entire time, I have been dealing in one way or another with internet security. Okay? It's an ongoing battle. We have a lot of experience from that. Some of it very painfully gained experience. Some of it experience grounded in base principles that we build up. Okay? But we have a lot of experience to share. One of the things we've done, over a year ago, we published a paper. If you have not read this paper and you build or consume devices, in other words, everyone in this room, you should read this paper. ak.ms/7 properties. The 7 properties of highly secured devices. And what we frame is a set of requirements and we bring together vocabulary from ourselves and from across the security industry to how to think about security of an IoT device. And here's the kind of the nugget I want you to think about. If you build an IoT device, I'm going to contrast this with PC security. Okay, particularly kind of legacy PC security. In the legacy PC world, security matters, okay? But fundamentally, you know, if you have a PC and it's used in your enterprise, what you're assuming is you have a human that is the agent of your business. And it's that human's responsibility to make sure that that PC is doing essentially the right thing. And then the PC is just a tool. Okay? But in a world of IoT, these devices, they are the autonomous agents of your business. They're executing business logic. They're doing things. They're interacting with your customers on your behalf. You deeply care about what the security of those devices looks like. And so we have these 7 properties: hardware-rooted trust, defense in depth, small trusted computing-based, dynamic compartmentalization, online failure reporting, certificate-based authentication, and renewable security. All 7 of them matter. Now, we use this word properties very specifically. I don't say principles, I say properties. And they're properties because a property is something you can measure. You can look at a device and you can ask the person who built that device, and you can ask them a set of questions and measure, does this device have a hardware root of trust or not, for example. Okay? And you can have an intelligent conversation about those 7 properties. And I assert that you need all 7 properties if you are to have a highly secured device. Okay? And the paper discusses more. Let me drill into a couple of these properties really quickly. And I'll point out that some of the properties of the 7, some of them are purely hardware specific. It's a property that needs to be built into the hardware, and if it's built in the hardware, you're done. You don't have to worry about it anymore. Okay? Some of them require hardware and software, so it's hardware cooperating with, say, the operating system running on that device, and some of them require hardware, software, and cloud in order to achieve the full property. Hardware-rooted trust. Fundamentally, here's the way to think about it. I'm going to create a device, and I'm going to send it through my distribution and sales channel out into the wild, and my customer is going to buy it, and they're going to connect to the internet, and it's going to come back and connect into my enterprise as I create new experiences for the customer and new business models. There are some things I fundamentally want to know about that device. One of them, I want to be able to identify that device. I want to know that it has a unique identity that is cryptographically protected so that that identity cannot be stolen, forged, or otherwise compromised. A second thing I want to know is I want to know that it's running the software I put on it, that it hasn't been modified somewhere in the distribution chain or by the customer, because as I pointed out with the stove example, I don't want my stove turned into a bomb. Okay, so I want to know that it's running the software that I put on it that's going to guard the integrity and protection of that software. And then, so that's the secure boot. So the device is up, it's running, it's been booted. Okay, days, weeks, months, who knows have passed, and now the device is going to connect to my enterprise. When it does, I have a point now where I want to know that it's still running the code that I put in it, that hackers haven't somehow come in through a buffer overrun and injected some code into it and modify its behavior. To do that, I need a property called hardware attestation. I need the hardware to actually be able to go measure at that instant what code is running on that device, sign that with a private key that's only available to the hardware, and give that key back to me so I can prove that it's running what I want it to. And if it's not, force the machine to reboot and restart back to secure boot. Okay, these are 3 properties that have to exist in your hardware. If they don't exist in your hardware, it does not matter how much software you add to that device. You can add gigabytes and gigabytes of software, you still are not secure because you still don't have a hardware root of trust. Okay, so fundamentally you have to have that. Now, another property, one that is hardware and software, is dynamic compartments. In other words, and there's multiple instantiations of this. It could be processes in an OS. It could be virtual machines on a hypervisor, but separate containers where I can segregate code so that a bug in one part of a code doesn't propagate to another part of the code. That requires hardware that knows how to create barriers and software that knows how to configure those barriers into compartments. Okay, that's an example of a hardware and software property. And then the cloud. So there's other properties. So let's think about renewable security. This is a key component that is software update. The device being updated so that either when I discover that there's a bug in the code that I can fix it, or if someone discovers an entirely new way of attacking devices, that I can create a mitigation and distribute those to my devices. It requires 3 things. It requires the cloud, because the cloud has to provide that update. Okay? At least if I want to do it fully autonomously without rolling trucks and people, I have to have the cooperation of the cloud. I also have to have software on the device that knows how to robustly apply that update, particularly make sure that it doesn't destroy itself in the process of doing it. Okay? And the third thing is I need hardware that supports rollback protection. Now, rollback protection is a rollback attack is a particular form of attack where a hacker, let's say you have version 1 of the software, you discover vulnerability, you update, you send out version 2 to all your devices, they all get updated. What do hackers do? They will try to figure out if there's a way I can trick the device into rolling back and using the old version 1 software, because I already know where the vulnerabilities are in the version 1 software. The only way to prevent a rollback is if you have hardware in support to prevent that. Okay? So this is where you need all 3 working together in order to have a robust, reliable hardware update mechanism, or software update mechanism. Okay? Now, those 7 properties, that is an awfully high bar. Okay? In fact, I would assert, especially in the MCU space today, with existing technology that's out there, it is an impossibly high bar. Okay? But it is the bar that your devices need. Okay? Azure Sphere is a solution that allows any device manufacturer who's building MCU-based devices to build devices that have all 7 properties of a highly secured device. And we talk about the value of Azure Sphere using 3 words: security, productivity, and opportunity. Now, security is we provide the basis and provide the ongoing support of these devices being fully secured with the 7 properties for the entire lifetime of the device. And we assume the responsibility for keeping those devices fully up to date in their security and keeping those 7 properties on that device throughout its lifetime. From a productivity perspective, if you've ever done an MCU programming or you have friends that do, you'll know that the tools they use for programming those MCUs are very firmly grounded in the 1970s. Okay? What we've done is we've brought the full power of Visual Studio, the Visual Studio team services, the full Visual Studio ecosystem to MCU-based programming for the very first time. And that's going to see those developers see an incredible boost to their productivity and reduce their time to markets. And then finally, opportunity. We have created chips that not only give you the ability to have confidence and trust in your devices because they're secured, but also additional processing power that allows you to create new experiences. That's what we offer with Azure Sphere. Okay? Now you may be sitting there saying, That sounds like an impossibly hard thing to do. How the heck are you going to do that? Well, let's talk about the details of how we're going to do that. Okay, it's an end-to-end solution that consists of 3 components. First, the Azure Sphere certified MCUs. These are MCUs, chips that will be built by our silicon partners. Each of these chips incorporates Microsoft silicon security technology that we've developed that goes into those chips, and they provide a secure, dependable hardware root of trust. On top of those chips, we have a new operating system that we've created, the Azure Sphere operating system. It's a highly secured operating system that is maintained and improved throughout the lifetime of the device by Microsoft and provides a highly secured software environment on those chips. And then finally, the Azure Sphere Security Service. And the Security Service, its job is to guard every Azure Sphere-based device and keep them secure throughout their lifetime. It does 3 critical things for those devices. Going back to the 7 properties, it provides certificate-based authentication, online failure reporting, and renewable security. Now, the way it does that is, or what that means is, it brokers trust. Okay? There are no passwords on an Azure Sphere device. All of the communication, all of the authentication, all access to privileges is performed through certificate-based authentication. And the Azure Sphere service provides that service for every device. It does device-to-device and device-to-cloud communication. Also, it provides ongoing detection of emerging security threats across the entire Azure Sphere-based ecosystem through online failure reporting, and we renew security through software update. Now I'm going to drill down in each of those components in a little bit more detail. So let's start with the MCUs. Okay, now an Azure Sphere MCU starts design life looking like any other MCU. It's got some I/O capabilities. It's got a Cortex-M, at least in ARM versions of these chips. There'll be a Cortex-M, a real-time processor to run safety-critical code on those devices. Okay, and then we add 3 things that uniquely make it an Azure Sphere chip. First, connectivity. So each of these chips has some form of connectivity built into them. The very first generation of chips have Wi-Fi connectivity built right into the chip. It's not an add-on, it's part of the core chip. Second thing is, each of these chips is secured by Microsoft technology. And there's 2 aspects of that. First one is what is known in the industry as an IP block. For those of you who write code, it's a library. It's a silicon library that we give to the device manufacturers for them to, we give to the silicon manufacturers for them to incorporate into their Azure Sphere certified chips. This provides the core of the root of trust for every Azure Sphere device. And then there's a set of firewalls that go inside the chip. So the chip itself has multiple layers of defense and depth. So if someone, say, does manage to break into one part of the chip, they're not able to get any further. Okay? And then the third aspect that is unique to an Azure Sphere MCU is that they are crossover chips. We have taken, and working with our partner ARM, we've figured out how to take the same Cortex-A class processors that you find in smartphones and tablets, and to shrink one down small enough that it fits into the power and cost budget of an MCU chip and bring it into the chip. Now, in doing that, we've slowed it down significantly. So instead of running at like 1.1 gigahertz or above that you would see typically with a Cortex-A7, it runs at a maximum speed of 500 megahertz. By doing that, we're able to significantly reduce the footprint of that chip, of that processor, and bring it into an MCU class chip. Some of you that have deep MCU experience, you're looking at this and saying, my gosh, that thing is huge for an MCU. Yes, it is. Guess what? Moore's Law works even for MCUs, okay? And it will be very economical, okay? But that gives us an amazing amount of power. One, having that sophisticated processor means that for the first time in an MCU, instead of running an RTOS, which is not secure, I'm going to make you all stand up and chant, an RTOS is not secure in a few moments, okay? It also means, so we can run a full operating system, but it also means that we've got additional processing power. And if you have a device that's never been connected before and I'm going to add connectivity to it, I'm going to want to enable new experiences and build new things on that chip. And I'm going to need processing power. Say processing power for ambient intelligence, for example. These chips have it for the very first time. Okay, now we are not getting in the silicon business from Microsoft of producing our own chips. Okay, in fact, this MCU space is very, very broad. There are literally dozens and dozens of MCU chip manufacturers. In order to provide the reach that we want, which is we want to make sure that every MCU device has all 7 properties of a highly secure device, we are disseminating our silicon technology out through the industry. We are licensing the Pluton security subsystem and the architecture for an Azure Sphere chip royalty-free to anyone that will take it. Even if they don't want to build an Azure Sphere certified chip, we will still give them the IP to put in their chips. We are fundamentally committed to making the world more secure. But we have dozens, we have a dozen here listed partners who are at various stages of their planning and preparation to bring Azure Sphere certified MCUs to market. Okay. Now, on top of the silicon, we run a new operating system, the Azure Sphere OS. This has been optimized for IoT, security, and MCU agility. Okay. It is a 4-layer operating system, and I will contrast this with an RTOS that you would see typically on an MCU. An RTOS is basically a library of code that you link with your application. You have a single layer of protection on most RTOS-based devices. In some more sophisticated chips, you have 2 layers, and that's it. This is a 4-layer system because this is what we have found is if you were going to build highly secure devices that are out there by themselves, they need to have that many layers of protection in the software architecture. The first layer is a security monitor. Its job is to guard the integrity and access control to resources across the chip. If you're familiar with the way cloud computing is implemented, you have a hypervisor that runs on each device, and then you build up from that. This is very analogous to the hypervisor you see in the cloud computing, okay? Only optimized for these very, very small chips. Above that, we run a custom Linux kernel, okay? Now, people will ask me, why did you use a Linux here? One really simple answer. Because the Linux kernel is open source. We want to enable every silicon manufacturer in the world to innovate as aggressively as they possibly can. By giving them an open source kernel, they don't have to come to Microsoft and convince us that some new silicon feature they want to do is worthy of our time to invest in. They can go put it in our kernel themselves, submit the pull request back to us. We will take the pull request, we will vet the code for quality and security, and work with them to make sure that it hits our bars for those. And then we'll bring the code in and we'll use it in the binaries that we produce for their chips. Okay? Now, above the kernel, we run an on-chip cloud security services. These provide update, so the full implementation of update both for the operating system and for the applications above, provide authentication, and they provide security for the connectivity. Then finally, the very top layer, the 4th layer, is where we begin to see the device manufacturer's code. It runs in sandboxes. Okay? We have 2 types of sandbox. We have a real-time sandbox that runs on the Cortex-M, on the real-time processor. That's where you would run your safety-critical code. And then we have containers that run, sandboxes that run on the Cortex-A cores. And those containers, you can have multiples of those, and those would contain your ambient intelligence code, your general purpose computation, your connectivity, your communication code, etc. Okay? And that factoring allows you to create a highly robust system with a high degree of security. Okay? And one of the things around those containers we have what are called in the OS community capabilities that label which container is allowed to do what. So one of the things, for example, the communication container, you can actually say which DNS addresses is this container allowed to communicate out in the internet. So for example, you can tell, hey, it's allowed to talk back to my enterprise on these ports, okay? And let's say a hacker somehow manages to get into your code and compromise it. Well, they can't turn it into a botnet that's going to go attack the DNS servers because they don't have access to those ports. They're not able to communicate on those ports. Okay? So it's all about building in as much security as we possibly can, and particularly trying to remove as many security concerns from the mental load on the device manufacturers. Okay? Now, final piece of the architecture of the solution is the Azure Sphere Security Service. Security Service connects and protects every Azure Sphere device. As I mentioned, it's doing certificate-based authentication, so it protects the identity of the devices and secures their communication. Using online failure reporting, we are able to detect emerging security vulnerabilities. What we've found at Microsoft, by the way, side note here, is that when an attacker begins to attack a device and try to figure out a vulnerability, they will cause anomalous behavior in that device. And so if we monitor the device for anomalous behavior, we can report that back, and we can often figure out what is going on with the device, how it's being attacked before it has even been compromised. And if not, then at least after part of it's been compromised, be able to collect enough data that we can figure out how to mitigate against it. We found it's a critical aspect of effectively your ecosystem immune system. And then finally, we respond by providing updates to the devices, and we do software updates, both of our operating system and for the applications that run on the device from the device manufacturer. Now, as I mentioned, Microsoft has two superpowers I serve. One of them is proven superpowers. Okay? One of them is security. The other one is developer productivity. And we have brought that full, rich Visual Studio experience to Azure Sphere device. I'm not going to go on belabor this point because Mike's going to come up and show you what that experience looks like, and you can get a full feel for it. The solution has 3 components, 1 low price, no subscriptions required. Okay? And so what effectively will happen is you want to build an Azure Sphere-based device, you'll go to your component distributor, you'll buy an Azure Sphere certified chip, and coming with that will come a license. The Azure Sphere license, which includes license to our operating system, including 10 years of support in the base version of the license of that operating system. So whatever security improvements we come up with, everything coming, we actually deliver it onto your device, and 10 years of service for the security service. That's all included, one price, one and done. Okay? And our motivation for that pricing model is to make it a really simple decision. Do I care about my brand? Do I want to build a highly secured device? And then I don't have to answer on the month-to-month basis, gee, this month do I care about security or do I feel lucky? Okay, one and done. This is a robust ecosystem, and we want to facilitate that ecosystem as much as we can. Azure Sphere is open. Okay, there's 3 key ways it is open. First, as I mentioned, we're licensing the silicon IP royalty-free. We want to enable any device or any MCU manufacturer on the planet to create highly secured chips. Second, it's open to any cloud. Now, our Azure Sphere security service does run in Azure data centers, okay? And every Azure Sphere device will connect for its security services for updates and certificates and error reporting to our Azure Sphere service. But for other IoT and other cloud services that device consumes, like say command and control, telemetry, backend ML, things like that, well, you can connect that device to any cloud that you want to. Okay? We'll secure the connection for you, but you can use whatever cloud. You can use a private cloud, you can run it on your proprietary servers, whatever you need, or you can connect to AWS or Google or IBM or anything else. I'll take questions at the end, okay? Oh, and then, let me back up. And then the last aspect of the open is, as I mentioned, we're open to the innovation from the silicon partners. As they create new features, we're going to bring those in. We're not going to gate them, as has happened with some other operating systems, okay? When we talk about the value proposition, and we've been out talking now for device manufacturers for 2 years, a select set about Azure Sphere. And we find that 3 words and 3 properties of Azure Sphere resonate with them: security, productivity, and opportunity. The security, Azure Sphere allows you, without any security expertise, to have a device that has all 7 properties of a highly secured device. And so that gives you peace of mind. Okay? Productivity, the Visual Studio tooling that we've created around Azure Sphere, the programming model, the code model around Azure Sphere is going to allow these companies to have, everyone building these devices to have much higher productivity. Okay? And opportunity, these chips do two things important in terms of opportunity. First, they give you the confidence that your device is trustworthy, that it can in fact be a reliable, dependent, autonomous agent for your enterprise. And second, they give you power that you've never had an MCU class chip before. And that's the power that you need to enable new experiences and new business models. The very first Azure Sphere-based devices will appear on shelf before the end of the year. Now, would somebody like to see some code? Okay, Mike, let's see some code, man.
Okay, shall we write some code? Who said yes?
Yes. Yes.
Who said no? All right, so let's get started. I'm going to be using Visual Studio 2017. The only thing that I've had to do here is install the Azure Sphere Visual Studio extension that adds in support for application templates, the build model, deployment, debugging, and so on to Azure Sphere devices. So no additional setup needed. I've got an Azure Sphere board that's connected to my laptop on USB. I'm going to be using a code snippet tool to accelerate writing code, because otherwise you'd be sat here for an hour just watching me type, which is obviously not ideal. Okay, so let's get started. I'm going to select File, New Project. And inside of Visual Studio 2017, under C++ cross-platform Azure Sphere, I can create an application from one of many different application templates, starting with a blank application, which obviously just gives me the skeleton of my app, and then I layer the additional code on top of that, or directly into something like Blinky. Like if any of you have ever built anything for an embedded platform before, the first thing you want to do is turn on an LED, right? It's the hello world of embedded development. So there's a Blinky app in there. There's a UART app for sending and receiving data on one of the UARTs. There are 4 UARTs on the board. There's an app template for connecting to Azure IoT Hub, but we're going to do that in this session anyway, so we can skip that. I'm going to use blank application just to get started. My application name is going to be app2, which is fine. Okay, so what we're going to do here is layer various pieces of code onto this blank application to show you how application development happens and how we can layer in support for things like Azure IoT Hub and Azure IoT Central into this application. So let's take a look at what's just been generated. This is the core code for the application. There's a file here called MT3620 RDB reference board, reference design. This contains the definitions for the GPIOs, UARTs, and so on that are used on this particular board. As we come down into the application code, what we'll see is a Boolean that is termination requested false, a termination handler that takes a signal and then flips termination requested to true. We'll come back to that in a second. And then the main entry point for the application. In here we can see a log debug for the application starting, and then registering a sigterm handler. This is basically a termination handler for the application. Why might the application get a signal to terminate? Well, there could be a number of reasons. I may have sideloaded an application onto the device that is currently running, and now I want to deploy a new application from Visual Studio, in which case the current application will need to be shut down so that the new application can start. Or maybe I'm using the over-the-air deployment model to push a new application to the device, in which case the current application will need to shut down so that the over-the-air deployment application can start. So let's get into the main loop of the application. We set up a time spec structure that has 2 parameters, 1, 0. The first part being number of seconds, the second part being number of nanoseconds. So in effect, what we're describing here is a 1 second tick, if you will. And then the main loop of our application is really simple. While termination has not been requested, output log debug hello world to the Visual Studio output window, and then sleep for 1 second. That's basically the application. So I should be able to build this application. I can hit F5 or click the play button in Visual Studio. And then that application will be deployed over USB to the device. I can see the activity light going on the board. And then the application will get started. And there we are. In just a few seconds, we've seen the application start. We can say hello world to the output window. Amazing, right? There's more. Okay, so that's literally hello world, right? So I can do everything that you would expect to do in Visual Studio. I can set breakpoints in the code, the breakpoint fires. I can look at locals. I can look at call stacks. In a multi-threaded application, I can look at the state of the threads. I can look at memory. I can single step. I can step into, step over. All the things you would expect to be able to do if you're writing, desktop code or Azure code. I can do right here on an Azure Sphere application. Okay, so let's extend this application. The starting point application is pretty straightforward. The board that I'm using here, and I think there's a board here that I can use as a prop. The board I'm using, you can pre-order these today, they're $85. The board has 3 buttons on it, button A, reset, and button B. And then down in the bottom left corner of the board, there are 4 LEDs, LED 1, 2, 3, 4. And they're RGB LEDs. Each of the channels, red, green, and blue, are controlled from a different GPIO line, right? So what I can do is write code so that if the button is pushed, I can flash the LED, in effect, to get me blinky, right? So let's go write blinky based on the blank application. What I'm going to do, whoops, I didn't mean to get rid of that. I'm going to just drop in at the top of the application a couple of ints for the handle for the button and for the LED, and then some booleans to control whether the LED is on or off and whether it should be flashing or not, and a counter to count every millisecond tick in the system, so when we get to a second, we can flip the LED on or off, right? So fairly straightforward stuff. Okay, let's come down to the end of the application. I'm going to drop some functions in here, some of which are currently commented out, but we'll come back to those a little bit later. The interesting function here is a function called set up GPIO and LED. So we're going to call this in the main function to get the handle to the button and to the LED. So we're making a call to a function here called GPIO, open as input, and here's one of those definitions from the reference design header, MT3620 button A. If I right-click on this and do a peak definition, what I can see is that this is GPIO 12 in the system. That's pretty important to know, and we'll see why in a second. Slightly further down is GPIO open as output, RDB LED 1 red, and again, if I do a peak definition on this, we can see that this is GPIO 8. Also important to know. And the reason why these are important is I need to come into my application manifest, and under GPIO, I need to put in the 2 values, 8 and 12. Because if I don't do this, and I build my application and deploy my application, and try and get a handle to those 2, to the button and the LED, that will fail, because I didn't request access to those within the application manifest. This is part of the security story that Galen was talking about a little bit earlier. So I'm going to put in 8 and 12 to the app manifest. I'm going to leave the app manifest open because we'll come back to that in a short while. Okay, I'm going to get rid of the breakpoint. We don't need that at the moment. And what I'm going to do now is basically replace main with a slightly different version of main. Okay, so the new version of main is almost identical to the previous version. We output a log debug message. We're now calling setup GPIO and LED. Our time spec structure is no longer 1, 0. It's now defining in nanoseconds a 1 millisecond tick as opposed to a 1 second tick. Because what we're going to be doing is reading the state of the button GPIO to see whether the button has been pushed. And if it has been pushed, then we'll kind of either turn the LED on or off, right? Okay, in the main loop, we call a function called test button state, which will return true if the button has been pushed. And then we flip one of our global variables for whether the LED should be flashing or not, on or off. At 1 second count, if we are flashing, then we make a function called to GPIO set value to set LED red on or off, depending on what its previous state was. Okay, so if I now build this application, F5, and deploy the application to the board, since we've set up in the application manifest support for GPIO 8 and 12, the application should build. The application should then deploy out to the board. The application is now started. I'll hold this up. Hopefully you can see this. If I push the button, we then get the LED flashing on the board. Can you see that? Yeah? All right. No, please. Please. Okay. Now we got Blinky, right? But wait, there's even more. What I've got here, and you may not be able to see this too well on this side of the room, is I've got a 28 by 14 magnetically flippable dot array, which is called a flip dot display. And that's connected on RS-485 to the Azure Sphere board. So what I'm now going to do is add in support for the flip dot display to the Azure Sphere application that we're writing so that we can then output some information onto that display. Okay, sound like a plan? Okay. So what I'm going to do now is go to header files, add, new item, and under header file I'm going to add flip.h, and I'll put in some function definitions here to initialize the flip.display. What this is going to do is create a new thread inside the application, and inside that thread we're going to request access to one of the UARTs, UART 0 in the system, which we'll then use to send out data over RS-485 to the display. And then we've got other functions, show a message on the display, set the cursor and get the cursor, which we'll come back to a little bit later. Okay, so I don't need this anymore. I'm now going to add a source file, add, new item, C file, and this will be called flip.c. Okay, I'll add that code in. This has its own font renderer built into it. The flip.display doesn't know anything about fonts, characters, numbers, or anything else. It's just a pixel display. So we need to be able to generate and send data to it. Okay, so I'm going to save this, close this, come back to main, and there are a few changes that I need to make in main. I need to uncomment the include for flip.h. And then when I come down into main, I need to uncomment the flip.init. This initializes the thread and also sets up communication on UART 0. And then we've got a comment here to do show message. So I'm going to start typing flip, and IntelliSense cuts in, right? So we've got the same level of IntelliSense in Azure Sphere as you would have for writing any other kind of application, right? So I'm going to say show message and something like secured from the silicon up as a message, and this will happen when we push the button, right? So that's all the changes I need to make in my code. Is there anything else that I need to do before I build and deploy the application? Yes. What? Yes, I need to make a change to the app manifest, right? Yes, because we're going to make use of UART 0. So in the app manifest under UART, I'm going to put in here, not that, in double quotes, ISU 0. Then I'm going to build the application, run the application, and the application will then get built and deployed out to the device. What do we see on the device, on the display? Okay, so 1:45 is the current time. Unfortunately, you can't see it over there. If you all want to kind of move across, you'll be able to see it. Okay, great. So we've now got time being displayed on the screen. If I push the button, the LED should start flashing, and we also get the secured from the silicon up message scrolling across the display. All right? Pretty neat, yes? Okay, good. But wait. Okay, so if you look in the center of the display, you can see hours, colon, then minutes, right? What's between the hours and the minutes? There's a colon that sat there, static, right? So one of the things that you might want to enable as a device maker is the dynamic enabling of features within a product that you've already shipped. So for example, who would take out a $1 a month subscription to have the cursor flashing on their clock. 2 people. I take credit cards and cash. Okay. So if we were to connect this device to Azure IoT Hub, Azure IoT Hub has this thing called a device twin document. So if I create an IoT Hub and then a device within IoT Hub for this flip-dot clock, as the IoT Hub owner, I can set properties for that device. So for example, I could set a property for the cursor being flashing or static. The device twin properties has 2 parts to it, one of which is called desired, the desired state that is set by the device maker, and one of which is called reported, where the device reports its current state back to the device maker through this device twin document. Does that make sense? Okay, let me show you what this looks like, and then we'll come back to this and implement the code. So I've written a desktop application as an IoT Hub owner that queries the IoT Hub device twin properties for this particular device, a device called Build 2018 for some reason. And what we can see here is that there is a desired state where the clock cursor state is currently false, not flashing, and a reported state where the clock cursor state is currently false, which means the clock has reported that it is not flashing. Okay? Within this application, I can set this checkbox, which will then make a change in the IoT Hub device twin properties within Azure that then get pushed out to my device, which is obviously connected to the internet, which will then implement that change within its software and then report its state back to Azure. Let's see that happen. So I'm going to come back to Visual Studio. I'm going to come into References, Add Connected Service. I'm going to choose Azure IoT Hub. Now I've got 2 options. You can see I can hard code a shared access key in my application, which we're going to do by using my Azure subscription to enumerate my IoT hubs and the devices within those hubs. Or if you're using IoT Central, which is a software as a service implementation, its IoT Hub does not appear within your Azure subscription, so you can just go get the connection key from IoT Central and drop that into your application directly. So we're going to use IoT Hub initially. So I'm going to choose Next. I'm going to choose IoT Clock Demo as my IoT Hub and Build 2018 as my device. Here's the connection string. I'm going to click Finish. This will add 2 files to my application, Azure IoT Hub.h and Azure IoT Hub.c. And you'll notice that we just got a message letting us know that the application manifest has changed. Now the endpoint address for the Azure IoT Hub is included in the app manifest, which means that the code to talk to Azure is now allowed to go to that endpoint, right? Okay, so now let's make a few changes in our main code. What I'm going to do is just uncomment the includes for the Azure IoT Hub functions and a callback for when the device twin document changes. In my application code, I need to initialize Azure IoT Hub, so I'm going to uncomment that piece of code. And I've got another counter inside of my main loop for once a second to make a call out to a function called Azure IoT do periodic tasks. And what this is going to do is query Azure, do you have any data for me? Or if there's a cache of local data, push that up to Azure. Okay, 2 more things that we need to do. Come down further into the application, there's a function called device twin update, which is the callback for when the device twin document changes. So let me just uncomment that, and then I'll explain what this is doing. So we've already seen in our desktop application, the JSON document has a desired portion and a reported portion. So this function, when it gets called, gets appointed to the JSON desired properties section. And what we do is query the version number, which is in effect just a unique number count for the message version that is being given to you at that time. And we also get the clock cursor state and store that. So what this code is going to do when it gets the state is convert the value to true or false, and then call a function flip.setCursor to set that value, and then report the state back to Azure. And the report state is simply a key value pair taking the value that we want to send, clock cursor state, and some JSON containing the value that we want to send back. So at this point, the code is now changed. We can build that application. We can deploy that application. We should see the time update because it's been a couple of minutes since we had the code running on there. I'm currently loading symbols. Okay. Clock's updated, yes. If I come back to my desktop application, I should be able to set flash cursor. We can see desired state is now true, and the reported state is also true, and you should now see that the clock cursor is flashing. Right? Simply by changing a device property in Azure and having that device property reflected down to the device. Right? This is a super simple demo of simply changing the cursor state on the clock, but obviously this could be any number of parameters. If it was a thermostat, you could set the desired thermostat temperature or whatever else through the same model. Okay, so just to prove this, I'll turn off the cursor, and that should then change the cursor state to false and the reported state to false as well, and the cursor stop flashing. Okay, now let's take this one step further. What I'm going to do is stop this application, close down Visual Studio, and open up a different version of the same application. So this application is still using some of the Azure IoT Hub functionality. This is using device twin properties so that we can set the cursor state as well. But it's also using Azure IoT Hub direct messaging, so we can send messages directly to the device from some other piece of code. And the messaging that we've set up in this application is the ability for this application to be connected to Cortana. So we can ask Cortana to set an alarm on the clock, and then have that alarm obviously fire on the clock. So the app is currently starting. And when that comes up, hopefully we'll see the clock appear. Is the clock up? Yep. Okay, so let's give this a go. The time is now 1:53. Hey Cortana. Hey Cortana. Ask Flip Display to set an alarm for 1:55 p.m. So we now have just about a minute to wait for the alarm to go off. So while that's happening, let me explain what is actually behind that. So the clock is the same clock code that we had running before, right? So that is connected to Azure IoT Hub, and IoT Hub has device twin properties. But Azure IoT Hub also has direct messaging. So something is obviously sending the clock a message to set the alarm, right? So here's the chain. At the front is Cortana, right? We ask Cortana to set the alarm. Cortana is connected to a bot developed using the bot framework. The bot framework supports multiple messaging channels. It supports Facebook and SMS and email, but it also supports Cortana as one of those channels. So what I'm doing here is asking Cortana to ask the FlipDot bot to set an alarm for a particular time. So the bot itself is connected to Lewis, the language understanding service, language understanding intelligence service, that has been trained on setting alarms, setting volumes, and setting time zones. In this case, we're setting the alarm. So there are multiple ways, and there we are, the alarm fired, right? So there are multiple ways that you could train something to set an alarm. Wake me up at 7, set an alarm for 7, make the alarm go off at 7. So there's a training model there. And what we extract from that is an intent, set the alarm, an entity, which is the time that the alarm needs to go off. We extract the alarm time, the entity from that, and then we send that as a JSON message through Azure to the FlipDot code running on the device, right? So that's how that part works. Got it? Okay. Great. So we've got our application running here. And One of the things that Galen talked about earlier was the ability to dynamically update applications that are running on devices. So one of the things that we can do here is have the ability to have an application that we've pre-written and pre-published update dynamically onto the device that is currently running right now. So let's go do that. If I stop Visual Studio and cancel out of this, what I'm going to do is open up a command prompt. We ship a number of utilities, command line utilities, with the Azure Sphere development tools that allow me to do things like set the device up on Wi-Fi or get the device ID, these kind of things. But we also have utilities that allow me to move a device from something called a device group where it doesn't get application updates to a device group that does get application updates. So let me spend a minute just talking about this. As a device maker, you may have multiple devices. Let's say you make coffee machines, for example. You may have a basic model, an intermediate model, and an advanced model. And each of these would be a SKU that you build, right? So in the Azure Sphere world, as the device maker, inside of our cloud utilities, you can create one or more SKUs to map to your devices. You can also create something called a device group. And a device group is something that contains devices of one or more SKUs that you can push out updates to. And there are multiple ways that you can think of having device groups. So you may think of setting up a device group for your internal test and development team. You may think of setting up device groups based on rings, like the Windows deployment model, or device groups that are based on region, for example, EMEA, US, Asia, and so on, right? And you can kind of mix. You can have region-based and test and development-based. When you set up one of these device groups, you can set a flag on the device group to either mark it as supporting over-the-air updates or not supporting over-the-air updates for your application. The OS updates will still come through anyway. So if you're setting up test and development device group, obviously it's kind of neat to be able to set up a device group that doesn't take over-the-air application updates, so you can constantly deploy locally from Visual Studio new applications and run them for some amount of time. So what I've got set up here is a script, which is called, let me type it, type set otg. .cmd. So what this is going to do is get the current sideload status of my devices up on stage. It's going to stop the application if it's running. It's going to delete the application from the device, so there's no application running on the device. And then what it's going to do is issue this command that you can see at the bottom here, which is a cutil command, a cloud utility command, to move this device, -A, the attached device, into a device group that supports over-the-air update. Okay, so by deleting the application off the device and having Visual Studio shut down, obviously the application isn't coming from me, it's going to come from over-the-air. So let's go ahead and run this set OTA device group. So this will get the status, the app is stopped. It will stop the app, it will delete the app, it will get the status, no app present. It will move the device from its current device group, which does not support over-the-air updates, into a device group that does support over-the-air updates. I'm going to hit reset on the board. Even though there's no application running on the board, there is a period of time where the board will periodically look for updates. So that could happen at several minutes into the future. By resetting the board, when it comes back on Wi-Fi, the board should then pick up the update on boot by connecting to Wi-Fi, connecting to the backend update service, and then picking up the new application. So the application that should be coming down is very similar to the previous application. It's a clock, and it still supports the device twin model that we saw before. The only difference is there's enough room on the display for the top line of the display to show the clock, and underneath it, the current weather temperature in Fahrenheit for Seattle. So that will take a minute or so to come down. Assuming that we get connected to Wi-Fi. We don't have an IP address yet. Okay, I'll leave that to go do its thing. And hopefully that will get connected to Wi-Fi, and then it will update the application. Okay, let's move on to the next thing. I bet you're all wondering what's under this cloth, aren't you? Okay, let me uncover this. So this obviously looks like an Altair 8800. So let me get this plugged in. And I'm going to run putty over here. Set this to COM3. Oop. Let me just get Device Manager to get my list of ports. Yeah, COM3. Okay, what I'm going to do is hit reset on the board. So behind the LEDs that you see here is an Azure Sphere board. And the Azure Sphere board has an I2C connected SparkFun TMP102 temperature sensor connected to it. Let me see if I can just increase the size of the text here. Appearance change. And set this to 18. Apply. Okay, can you see that? Okay, so this is saying memory size 8192, terminal width 72, no thank you. So this is Azure Sphere running an 8080 instruction emulator, running the original Altair 8K ROM BASIC connected onto putty being displayed in this window, right? But there's even more to it than that. You may have seen the LEDs flashing on the front of this. As I'm doing things here, that is the 8080 opcodes being displayed on the front panel as the application is running, right? So this is running 8K ROM BASIC. We're all about back compatibility at Microsoft, right? This is Microsoft's latest technology, Azure Sphere, running Microsoft's first technology, 8K ROM BASIC, right? So I can type things like print, hello, and that prints hello, right? So it's real basic code running here. We've overridden two commands in the basic library. So I can type cload. Let me first of all prove that there's nothing here, right? List, there's no app there, right? So I can type cload. Or actually, if I could type cload, cload program A, and that will load a program from memory on the Azure Sphere into the 8K ROM BASIC space. And then I can type list, and this will list the basic application out to the console, right? So this is a basic app that has been written to run on the 8K ROM BASIC on top of the 8080 emulator running on top of Azure Sphere. Right, so we've overridden cload to load the basic application from Azure Sphere. We've also overridden csave. Can you see line 210 there on the screen? Line 210 says csave star T. So what this is doing is we're reading the TMP102 temperature sensor connected to I2C on the Azure Sphere device. And in 8K ROM BASIC, there was a port model, so you could read or write into ports from BASIC. So we're exposing the temperature through two of the ports as high byte and low byte, into the basic application. And you can see that on lines 105 and 115, input 42, input 42. And then we convert those two raw bytes into Fahrenheit. We print out the current temperature to the console, and then we call csave star T. csave is cassette or tape, but we don't have a tape here. What we're actually doing instead is outputting that data directly to Azure IoT Hub, right? So now we have the original 8K ROM BASIC writing code in BASIC, connecting to Azure IoT Hub and displaying temperature data from the temperature sensor connected to the Azure Sphere device. So let's go ahead and run this. And you should see the LEDs going on the front as the opcodes execute. And with that running, we can say, oh, beer temperature is 71 degrees. That's obviously a little warm for beer, unless it's British beer, in which case that's perfect, right? Oh no, our beer is a little warm. So if this is connected out to the web, what I should be able to do is open Azure IoT Central. Should be able to go to my device list and then to Altair 8800. And then I should be able to look across the last hour. Nothing in the last hour, during the last day. And here we can see temperature data output from the Altair 8800 from that basic application through Azure IoT Central graphed directly into here, right? So that's pretty cool. So this didn't update because I unplugged it in order to plug this in. So what I'm going to do is disconnect this, reconnect our original board so that has a chance to get on Wi-Fi and get updated. And we have about 9 minutes remaining, so Galen, do you want to come up? At this point, demos are about done. Let me switch back over here.
All right, so we wanted to remind you, the dev kits, so dev kits will be available in September publicly. You can pre-order today to get your place in line so you get one. And we want to take questions. So we have 2 mics open. If you want to come to a mic so that everybody can hear you, we'll take some questions while we wait for the... There it goes. Okay.
I didn't touch anything.
All right, question? First question.
Yeah, so we built a device that already uses like a hybrid FPGA and processor SoC. I'm guessing it's probably not already part of your Sphere compliant device list. Is it a way to make it compliant by using a compliant MCU as the gateway I/O for everything?
Yes, you can do that. So if you want to take, you can get a chip and you can put it together, and kind of like we've done some of the things here, and build a fully secured device. One of the things we encourage you to, if you do that, to think very carefully about the update model of the code. So you could actually push the updates through our channel, through Azure Sphere, and then deliver them there. And there's some caveats there, but in terms of making sure that you do that is in a highly secure way. But you can, it's a common scenario, let's put it that way. Okay?
Thank you.
Yes, over here.
So you sort of beat down RTOS. I'm just wondering about determinism in the performance.
Right.
Could you speak to that?
So an RTOS as a library for real-time deterministic performance is awesome. An RTOS is a communication connected to the internet thing, not so awesome, okay? And so we have those Cortex-Ms, and those Cortex-Ms, you can bring whatever RTOS library you want to, or we have one, and run it on the Cortex-M, and you have fully deterministic computation there. So you can do exactly what you've always done with the microcontroller on those Cortex-Ms, and then you put your communication code and your other code over on the thing. And part of, you remember when I showed the chip, there were the firewalls inside the chip? We actually firewall off that Cortex-M so that it is, so we know which GPU, which I/O capabilities it has, but it can't touch anything else in the board other than what it's supposed to. So we think we've got a good answer for you. Over here.
2 questions. First one is, so you mentioned push of properties initially, but the examples were all polling based. Can you actually push out to a device? Because 100 million of them polling could be quite expensive.
Are you talking about the device twin type properties?
Yes.
Yeah, so the properties are set in Azure, right? So you set up your IoT hub, you set up your devices within IoT hub, you then set up your properties within the device twin properties for those devices that are there. The code that I've written here is calling, in effect, Azure IoT do work on a 1 second tick, right? But that can be set to any time period that you want it to be, depending on how you're connected. So in a partially connected world, where connectivity may not be guaranteed, when you see connectivity come in, and there are APIs in the OS to query, do I have network connectivity? At that point, you would make that call and do the exchange of data, right? So your code can say, I want to send these messages, and have them in effect queued up for when you do get connected, and then you do the push-pull at that point.
Right. Second one was, so your slides mentioned a 10-year lifetime for your devices. So what happens if on year 11 some vulnerability gets discovered? What do you do then as a as a manufacturer?
So we have two options that happen at the end of, and there's the period that the manufacturers buy from. And if they don't extend that period, what happens is we will actually disconnect the device from the application from the network. We reserve the right to keep servicing the operating system, but the application it'll go into a disconnected mode. And all these devices have to be able to operate somehow in a disconnected mode. So that's the way we deal with that. Okay. All right. Question over here.
Hi.
Hello.
If you can go back to the Azure Sphere OS architecture. So typically what we understand, or what specifically I understand, is you would have the hardware. On top of that, you would have the OS, which includes the kernel also. And then any security services would sit on top of it. But if you see in this particular case, we have a hardware, which is an MCU. I'm sure they might not be running anything on the MCU. And immediately you have a security monitor. So my question is, how can an OS layer run when a kernel or a base operating system is not there on the device?
So the device comes with the operating system on it. The full stack is already pre-installed on the chips. Is that your?
So if an MCU already had an OS, which means that the OS had a kernel also.
Oh, you mean if it wasn't an Azure Sphere chip?
In general, a hardware will have a OS, which has basically a kernel also.
Right.
But in this case, I see between the OS and the MCU, there is a security monitor. So how can a security monitor, which could be an application which is running, can run directly on an MCU without an OS?
Okay, well, all right. So I think we should probably take this offline. I will say that the OS is that full stack, okay? And that is all in there. It's all integrated in, it's all in the chip.
And it's provisioned at manufacture time.
And it's provisioned at manufacturing time, okay? So the customer doesn't load this on. This gets done, or an end consumer. All right.
Thank you.
Over here.
You mentioned that the chip is basically connected to Azure, to Microsoft for OS patching and updates, and to the IoT app for the application level. So, question first of all, how do you ensure customer privacy? So customer concerned that no telemetry, nothing has been sent to Microsoft. Then the second thing about how do you determine when you do an upgrade? I mean, how do you don't affect the service? I mean, Microsoft decide to do an upgrade and then stop the service of the customer? How does it stand?
Okay, I want to make one thing clear. So in the base Azure Sphere, there's no Azure IoT. What we've done for these demos, we've added Azure IoT. Okay, so and at the Azure, you would implement your privacy features in the device before you send the data off to Azure IoT, right? So you'd have what are the customer security requirements, and you decide what they are the customer privacy requirements. So you would implement that in there.
Can I add to that?
Yeah, go ahead.
So when you're writing the application, for example, when we're building this device, there were certain things that we wanted to know about the runtime of the system. So in effect, we built our list of telemetry items that we were interested in, and then we connected this up to the App Insights, Azure App Insights, so that we can then from here emit that data to App Insights, and then we can view that data.
So I assume basically you on the device you set up Windows time when the device is actually going to Azure Sphere and checking when is update available.
So there's two separate pieces. One of which is the update of the operating system and application, and that's independent of the application running and emitting its telemetry that you decide upon to wherever you want to send that, right?
Yeah.
So Microsoft is not collecting. I mean, beside RAM, CPU, it doesn't.
No.
We're not. Azure Sphere does not collect user data.
So and then when you decide when you update the OS without affecting the customer service.
There's some controls in the app that the app can say, hey, we're not quite ready. We need to finish something before you can do an OS update. Okay. All right. I think we have time for one more question. Yes.
The code you demoed today was targeting the Cortex-A.
That is correct.
Can you talk to me about what's possible for targeting the Cortex-M?
That's coming.
And timeline?
We're not announcing that yet.
No comment today.
It will look the exact same though. We will have the full.
So Visual Studio.
We'll have the full Visual Studio experience for the Cortex-Ms as well.
Very good.
Okay. All right. Great. Want to thank you all for coming. And remember to fill out your feedback on your evaluation